Hi, my name is Isis, and I will be presenting on the research article Forward and Inverse Kinematics Model for Robotic Welding Process using KR16KS KUKA Robot. In the words of the author, this paper aims to model the forward and inverse kinematics of a KUKA KR16KS robotic arm in the application of a simple welding process. 20 years ago, it was predicted that robots would have a substantial effect on technology today, though they haven't exactly been as prevalent as would have been expected. So while they have many applications in advanced technologies, they're limited in what they're capable of doing due to their controllers, despite their manipulator arms being versatile. But despite this, they're still very complex. Robots are constantly evolving with new research and technologies, and though they were previously limited, now they have kinematic problems. They also have kinematic problems due to their multiple degrees of freedom and their multiple link space mechanisms. But now the trajectory of a robot can be planned by analyzing kinematic solutions while designing a robot, which is what we're going to be looking into today. Modern-day robots can simplify manufacturing tasks by implementing task-level controls, and this is done through kinematic control modules built into the robot as a hierarchical control system. Moving forward, just some keywords we're going to be discussing today. I'd first like to specify that the KUKA robot is just a German manufacturer of industrial robots. Now, forward and inverse kinematics, those are the analysis that we're going to be going through today. Forward kinematics can be used to calculate the position and orientation of the robotic manipulator in terms of the joint variables in order to find the position of the end effector. While inverse kinematics are the opposite, the joint angles can be calculated using a specified position of end effector using kinematic equations. The robotic welding process, simplified, is just two pieces that can be welded together using a proper setup and welding end effector. But using a new welding robot and robot automatic welding technology can be used in various mechanical fields, and welding tasks have various requirements, so further research and improvement is still being made on things such as welding seam tracking technology and advanced adaptive capability. In this paper, the kinematics and inverse modeling of the KR16KS arm are discussed specifically. Now, this robotic arm has a control panel with display and an integrated mouse. It has touch-up, which allows specific positions to be saved. Modules, functions, and data lists can be created and modified. It has a VGA interface and a controller area network, a Windows XP operating system, and altogether is a 6-axis robotic arm that weighs 235 kilograms with a maximum 16-kilogram payload. We're now going to go into the methodology and the analysis research and how forward kinematics and inverse kinematics are used to examine a simple welding process using a robotic arm. So in this research, we use a welding process workpiece used for the research. It's welded onto a flat metal sheet, and the rectangular block has these dimensions of 0.34 meters by 0.17 meters by 0.1 meters, which is going to be really important in our matrices that we're going to do later on. This picture on the right is also going to be used for the diagram, the operation flow and programming diagram that we're going to go over, and it shows how the robot will be moving to weld this piece. So an operation flow diagram is used before programming occurs, and once that programming happens, the programming of the motion is developed using the KUKA control panel on the robot. So starting in this top left, we're moving counterclockwise. This is just the motion that it's going through each point. So overall, it's going to move linearly along the workpiece sides, and when it gets to a corner, it's going to move circularly around that corner at a correct angle of welding and continue moving linearly. And at the top right, that's our final destination, and that is a space in the center above the workpiece where the robot can drill a hole through the center. So this is our robotic arm here for the kinematics analysis and discussion. On the right, these are just all of the joints and how we're going to be moving through them all. I'm not going to go through all of them, but essentially X1 is normal because those two axes are intersecting. X2 through 4 are in the direction of the common normal, and Z5 and Z6 are the same direction because they're parallel and collinear. Now Z5 also stands for the motion of joint 6, and Z6 is the motion of those end effectors. So that's what we're moving forward with. Now we're on to the DH parameters. Now these are used to select a frame for reference for the robotic arm, and it allows us to describe the location of each link relative to the previous one in between the joints. So 4 parameters are used for this, and we're going to have a table on the next slide, but the length Link length is the distance between the axis Z0 and Z1 measured along the Z0 axis. The link offset is the distance from the origin to the intersection of the X1 axis with Z0 measured along its axis. The joint angle is the angle from X0 and X1 measured normal to Z0, and the link twist is the angle between Z0 and Z1 measured in the plane normal to the X1 axis. So again, we're going to move forward. This is the table for all 6 joints and the parameters for the links and joints, and what we're going to be using for all of our matrices. This is our DH parameter matrix method. It's going to be used for all 6 joints. This matrix is a 4x4 transformation that uses the position of a point on an object and the orientation of the object in 3D space. So we're going to be doing various transformations using the forward kinematics. So here we see all 6 joints. We filled in the thetas for all of those values, and we're going to do some matrix math with those. So on the top here, you can see the total transformation between the base of the robot and the hand. And the equation for this is multiplying all of those A matrices. So these are the intermediate steps here with A1, A2 being multiplied, and so on and so forth. Our next intermediate step, I just have those final matrix values for multiplying A1 and A2, 3 and 4, and 5 and 6. And that leads us with that transformation matrix equation we went over before. We are left with a 4x4 matrix that we did kinematic analysis on. So all of these equations here are the variables you see in that final 4x4 matrix that we have made. So in a given reference coordinate system, the location of the end of the manipulator can be found using the given geometry of the robot and the parameters of the links and the variables for the joints. So for our forward kinematic analysis, the developed programming has a point-to-point movement based on the numbering shown here in this matrix, and we have 11 points of movement that are studied in the model as we move along the robot arm. These descriptions are used to determine how those transformations are going to perform while we're moving along the axis. So as I said, we have 11 points, and they're going to perform either Cartesian, spherical, or cylindrical. We next have a lot of matrices that I have to get through, so I'm going to be moving fairly quickly. But point 2 is performing as a cylindrical, based on that table that we just went over. And each of these points have a different movement. So this one is moving 0.17 meters along the x-axis, negative 0.5 along the z-axis, and it's rotated 50 degrees about the z-axis. We're then taking this final matrix on each of these points. We're going to be taking the final matrix here in the bottom right-hand corner and moving forward onto the next point. So here, point 3 performs as Cartesian. We're moving negative 0.34 meters along the x-axis. And again, we're taking the value from the previous slide and we're multiplying it to come up with an entirely new matrix. Moving on to point 4, which performs as spherical. The movements here are 0.2 meters along the z-axis. We're rotating 23 degrees about the y-axis and 27 degrees about the z-axis. And we're taking this final bottom right-hand matrix and moving on to point 5, which performs as Cartesian. And the movement here is 0.17 meters along the y-axis. And here's our final matrix. Moving on to point 6, which performs as spherical. There's an end effector movement here as its orientation angle is rotated by 40 degrees about the y-axis and 32 degrees about the z-axis, which is what you see here on this final matrix. So this is the one we're going to be moving forward with. Point 7 performs as Cartesian, and the only movement here is 0.34 meters along the x-axis, which leaves us with this bottom right-hand matrix. Moving to point 8, which performs as spherical. The movement here is through the end effectors as the orientation angle is rotated by negative 34 degrees about the y-axis and negative 35 degrees about the z-axis. Point 9, Point 9 performs as Cartesian. The movement is negative 17 meters along the y-axis. Moving on to point 10, we have 2 different steps here. Here's the second matrix. It's kind of blurry, but it's right in the middle of the slide. And that brings us to our last point, which is the Cartesian transformation. And the movement here is 0.12 meters along the z-axis. So our next step is the inverse kinematics analysis. Now the given references coordinate system is used in inverse kinematics to find the corresponding variables of each joint with the given location requirement of the end of the manipulator. So this process involves multiplying each inverse matrix of T matrices and equalizing the corresponding elements. So that's kind of confusing, but we're going to see it in the next few slides, the steps that are taken. But using the inverse kinematic solution allows us to use the value of each joint to place the arm at a specific position and orientation. So to separate the angles, we're using that RTH matrix that we previously saw. It's going to be pre-multiplied with the individual inverse A1 matrices. So we're calculating the value of each angle using the end effector position, which we went through earlier and can be seen here in the second matrix. But I circled the values here on the slide that we're calculating on the right hand in these equations. And as you can see, we can solve for theta 2 as well as theta 1 down here. Moving on, we have these other matrices also circled. These are the values that we're going to be using for the next equation, and we're pre-multiplying by the inverse of A1 to A3. So this is all really confusing as well. There's a lot of numbers, or rather letters, but on this next slide, you can see the equations that those equal out to in order to solve for theta 3 here in the middle of the screen, as well as theta 4. Here we're pre-multiplying by the inverse of A1 through A3, which you can see on the top, that top matrix equation. I also circled the values that we're solving for specifically. And here on the next slide, you can see that allowed us to solve for theta 6 as well as theta 5. So with all of that being said and done, here we have a summary of the angles calculated. So we have all the thetas in terms of their position and the orientation of the robot. So on the left hand, you see theta 2, theta 1. On the right, we have theta 3, theta 4. And on the bottom here, we have theta 6 and theta 5. So when all that is said and done, we have these total transformations performed. These are the same matrices that we've been seeing over and over. These individual variables, we have really long equations. But these were all of the matrices that we just performed. That brings us to our next slide. This is our final transformation matrix across those 11 points that we did throughout the welding process, which gives us a final matrix value. So in conclusion, what we have performed were forward and inverse kinematic models that were used to assess the robotic arm movement. We assessed all in all a simple welding task to weld a block onto a metal sheet, and before programming, a movement flow diagram was designed. 11 points of movement are used for the application of the forward kinematics, and DH parameters were used to form forward and inverse matrices for calculations of each movement, which proved that the KUKA KR16KS robotic arm could complete a simple welding task using these kinematics. Thank you. On this final slide are the references for the research article that I presented on.